Hi, everyone. Okay, let's start. 221, the second lecture or the second week of this quarter. So, hi, I'm Dorsa. You saw me last time. I'm co-teaching this class with Percy. And today our plan is to talk a little bit about robotics. So this is going to be kind of an informal introduction to robotics, a little bit of a history, a little bit of state of the art, some cool videos, and a bit of chat. So I don't need to finish my slides. I have a lot of slides. I'm probably not going to finish my slides. So feel free to interrupt me any point in time. If you have questions about anything, we can make this an informal discussion, again, at any point in time. I will probably not cover like all the things that are in the slides anyways. All right, so let's get into some quick logistics. All right, so this was our plan for the class. I'm sure you've seen this from the last lecture. So the plan was to start with reflex-based models. We've kind of already started that. So Percy basically went over the machine learning components last week, and we also have another week of machine learning, a little bit of deep learning. And then starting next week, we are going to talk about state-based models. So I'm going to cover a lot of that. So we are going to do search, MDPs, games. I'm going to reuse a lot of videos from last year, just giving you a heads up. We'll probably add and remove some, but last year's videos, they're in NVIDIA, we have a whiteboard, everything is great. So I'll probably reuse a lot of that, but we basically will plan to break them into modules. And then Percy will cover variable-based models, and I will finish logic and finish the class. So that was just a quick overview of what the plan is. If you remember, Monday lectures are not modules, right? Monday lectures are going to be guest talks and chats and having fun. So just to give you an idea of the Monday lectures, so this is a tentative schedule. We've already done the introduction to AI. Percy did that. Today I will be doing this talk on state of robotics, talking a little bit about what that is, why we should care about it. And then next Monday, we have a guest speaker. The guest speaker is Mariano Florentina Foiler. He is a faculty in the law school. He's also on the California Supreme Court. So it should be a fun talk to attend. He does a lot of work around AI and law. He does teach a class actually on regulating AI, and he has a lot of interesting opinions on that. So totally recommend showing up for that. I think that would be a lot of fun. Then the week after, we have Tatsu Hashimoto. So Tatsu is a new faculty in the CS department. He does a lot of work around robust machine learning, so he'll probably be talking about that. Followed by Percy, talking about state of natural language processing in week 5. By the way, this is tentative, so do not quote me on that. Some of these dates might change. I think the speakers are accurate. The dates might move around. And then finally in week 6, we have Emma Pearson talking about AI inequality in healthcare. She'll be a faculty at Cornell Tech joining next year, so it would be interesting to hear from her. And then week 7 is kind of like a fun chat just with Percy and I. We'll show up and you can ask us anything basically. We plan to think about like grad school and talk about like those topics probably. So if you have any questions about that, research what to do after 221, I think that's a good week to attend. Week 8, we have Yoav Shoham. So he was faculty at Stanford, and he has done a lot of work like from back in the days in AI, and he's, kind of like all the revolution of AI. So really fun to show up for his talk. And then week 9, we have Drago Angolov. So Drago is the head of autonomous driving at Waymo. So if you're interested in learning about autonomous driving to the extent that he can talk about it, that would be week 9. And then week 10, I will do a conclusion. So that is, and I'll wrap up the class. So that is kind of our plan for Monday lectures. I just wanted to advertise it. So, and you kind of like have a plan of what will show up next couple of weeks. Okay. All right. Any questions? If you have any questions, by the way, just put it on chat or interrupt. All right, so today we want to talk about robotics, and I just want to start it off. I have a lot of videos today, so there will be fun videos. I just wanted to start off by some video showing robots can dance, just to advertise this. You guys can hear this, right? Yeah, okay. Girls hit hallelujah, girls hit hallelujah, girls Anyways, I wanted to start with this video just to motivate why we care about robotics. This is Spot from Boston Dynamics. Boston Dynamics is a company that does a lot of really cool robotics type of work. We'll see more of their robots later in this lecture. But robots can dance, they're cool. And let's just start the conversation with this question of, well, what is a robot and when is it that we call it a robot? So question that I have, and I think maybe like it would be a good starter that we can just go into breakout rooms for 2 to 3 minutes, just chat about this. And the question that I guess I have is, think about a hammer. Is a hammer a robot? What do you think? And think about like Google or Google Home or like Siri. Is that a robot? So what defines a robot? And I think that's just the starter to think about like, what is a robot? Why should we care about it? And go to breakout rooms, 2 to 3 minutes. We'll come back, put your answers, introduce yourself, talk to the people in the breakout room, and then put your answers when you come back on chat, and we'll continue. Back?
Yes, I believe everyone's back.
All right. Yeah, so I hope you just met your friends and other people in the class. And yeah, if you have thoughts, put it in the chat. We'll look at it later. What is a robot? But let's actually continue with our talk today, because again, I have a lot of videos. So my plan for today is to do a bunch of things. I'm going to start with a quick history of robotics. Where did it come from? Why do we care about it? Then I'm going to spend a bit of time talking about why you should care about robots and why should this class care about robots. How are robots related to AI? What is the relationship there? And then I wanted to spend a little bit of time talking about robotics at Stanford. So what are the research that's done at Stanford? Who are the faculty who do robotics at Stanford? Just so you know the faces and you know what classes to take and kind of like what type of research is done and how you can get in touch with them. This is probably to the extent that I can get, but if I have time, I'm going to talk a little bit about some exciting robotics applications, like all the awesome things that are happening. Also all the not so awesome things that are happening, the fact that robots are far from perfect or just like not there yet. And then if I have time, which is very likely to not be the case, I will talk a little bit about my own research around interactive robotics. So again, the rules of it is at any point in time, interrupt, just ask questions, raise your hand, or we'll do that, and we'll go from there. And let's just jump into this quick history of robotics. Where does it come from? Where does the word robot even comes from? So the word robot actually is kind of old. It comes from this play from Karl Čapek in 1921. The play is called Razum's Universal Robots, and it's about basically these mechanical men that are built in a factory and are supposed to do work for humans, and then they rise against humans. So that's kind of like the plot of it. And basically it has a little bit of a dystopian view of that. And the word, these mechanical men basically are called robota, which basically means slave or kind of like labor type work in Czech. I don't know if anyone knows Czech, and I don't know how accurate that is, but that's basically what I read on Wikipedia. So I assume that is accurate. So that was the word robot, but then the word robotic was also first introduced by this guy, Isaac Asimov, who is a science fiction writer. And then he came around 1950s and he wrote a bunch of books about robots, and the view of it was a little bit nicer. It was a little bit friendlier than this dystopian view. And he talked about these different rules of robotics. So robots were there to help humans, and they were supposed to follow these different rules. So you guys might have heard of these 3 rules of robotics by Isaac Asimov. So the first one is that a robot may not injure a human being or through inaction allow a human being to come to harm. The second one is a robot must obey the orders given it by human beings, except where such orders would conflict with the first law. And then the last one is a robot must protect its own existence as long as such protection does not conflict with the first and second law. Okay, so kind of like this is obvious, right? Like you don't want the robots to go against humans, and you don't want the robot to kill itself. And these are kind of the three rules. And the reason I'm mentioning this is that people are coming back to these rules, like even these days. Like when people are thinking about robots, they feel like, oh, a robot should try to satisfy these three laws of robotics, and these are kind of like the core laws that need to be satisfied. And the thing about these laws is, sure, it is nice, but they're kind of obvious, right? And actually satisfying them is the most difficult part, and it doesn't really like go through that. Like if I have my robot running gradient descent on the loss function, how do I define that loss function accurately so I satisfy these rules? Like that is not a very obvious thing. And then I guess hit it and go and talk about that. Let me give you an example. So let's say I have Rosie the robot that's supposed to like clean my house, or I have a Roomba. That Roomba is supposed to clean my house. And let's say I have built this super nice, intricate house of cards, okay? Any human who's helping me clean my house would know that you shouldn't touch this house of cards because I spend so much time and this is so valuable to me, and you shouldn't touch it, you shouldn't go and clean it. But a Roomba wouldn't know that. Why would it? Like, why would it know what a house of cards is, or like how much energy I've put in creating it? So that is kind of like the objective function. And sure, it's not about harming. It might be harming me. It's harming humans. But in general, thinking about what should be the objective that the robot should satisfy, what should the reward function be? We'll be talking about MDPs in a couple of weeks, and we'll be talking about reward functions. What should the reward function be is actually a very difficult problem. This is an active area of research trying to understand what are the human preferences, what are the things that humans actually want robotic agents to do around them. And then at the same time, what does the robot think those preferences are? And there's a mismatch between that. There's always going to be a mismatch between that. And that mismatch, how harmful is that going to be? How unsafe is it that the robot doesn't know everything? And you might ask, well, why don't you just like write that as an objective that, hey, robot, don't go and destroy Dorsa's house of cards? Well, that's perfectly fine. But the thing is, like, it is really hard to write out all these specifications, all these properties that we would want to satisfy in the world, because there's just so much context, so much information in the world. And humans just know that, like as they grow up, like they learn and they know that. And robots wouldn't necessarily know that. And you might say that's just data, so let's just learn through that. A lot of people agree with that. A lot of people disagree with that. It's still like a point of debate. That is that just data? Like I just need to like show more things so the robot knows house of cards are important to Dorsa. Like that's also another view. But in general, the point of the slide is, hey, these rules of Asimov, like these rules that are put out there, they're not that obvious to satisfy. Sure, I can say don't kill humans, but it's not like really obvious how I write out like what does it mean not harming humans. And the second point I want to make here is that even that is still under question, the not harming humans. It's actually not obvious to everyone that we shouldn't use robots to not harm humans, which is a little bit silly in my opinion, but I'm just talking about everyone's opinion here. So like if you think about like our defense or other countries' defense, right? Like people use these things called autonomous weapon systems, which are basically like you can have drones that can detect targets and shoot at them. You can have lethal autonomous weapon systems. These are commonly referred to by laws, lethal autonomous weapon system, basically. And it's a big question. Should we use these? Should we not use these? When can we use like lethal autonomous weapon systems? And yeah, it's not like it is here. It's not a thing that's science fiction. It's actually a thing that our like basically U.S. defense has it. Like China, like the whole like all over different countries have some version of this. And the question is like, yeah, if we don't use it, like other countries might use it. And how do we think about like using or not using these systems? Like how do we put a ban even on it? What does a ban on it mean? And there's a lot of debate around this. Stuart Russell, who's a faculty at UC Berkeley, and he also teaches AI there. He's basically a proponent of banning, like fully banning lethal autonomous weapon systems. And he has a lot of interesting talks around this. We will talk about this a little bit more toward like in the conclusion lecture, but this is also something I wanted to mention because it could be an interesting topic to talk to Tino about next week. Like when you think about laws and regulating these things, how do the regulations like work and make sense? So yeah, so even like not harming humans, which is what Isaac Asimov said, like that is still like even under question here. Like it's not clear if that is what we want to do. But okay, let's go back to the history of robotics. Like, why do we have robotics? When did it start? So around like 50s and 60s, we had a lot of excitement around AI, right? So Percy was talking about AI last week, talking about the history of AI. And that was the time that there was a ton of excitement. And even Turing has this paper where in the paper he writes, the best thing we can do is to build a robot with TV cameras for its eyes and motors for its legs, and have it run around the countryside and learn from the world. So this is from back in the day, like Turing time, and this is what he was thinking. And like even in the same, like in the same paper, later in that paper, Turing says, well, this is too difficult. I don't want to deal with like this physical interaction with the countryside. So instead, maybe we should focus on the problem of intelligence. Maybe we should focus on AI. And that is how like the next 50 years was all about AI and building good AI systems. And there was a lot around robotics too. Like robotics also has seen a lot of advances since 50s. But a lot more has happened in the AI side of things just because the robotics side was so difficult. An example of that is thinking about Deep Blue, which basically won its first game against the world champion for chess in 1996. And it was doing like amazing intelligence, right? That is intelligence, being able to like win at this game of chess. But the thing that was happening was that the chess pieces were moved by humans because that was so difficult. Like grasping is still so difficult when you think about like a robot trying to actually like move these pieces. And that was not solved like in 1996 in any ways at all. Okay. All right. So when did the first robot come? So I've been talking about this history and like the question is, okay, so what was the first robot out there? The first intelligent robot. So the first intelligent robot was Shaky. I have a video of it here. It's kind of like a 5-minute video, so it's a little bit of a long video, but let's just watch it. I think it has a lot of interesting history in it.
Shaky was the world's first mobile intelligent robot, embodying numerous breakthroughs in artificial intelligence, robotics, computer vision, navigation, and other research areas. The robot was developed from 1966 to 1972 by SRI International, then called Stanford Research Institute, and its legacy and impact are still very much alive today.
Shaky's really the great-grandfather of things like self-driving cars and even military drones. The hardware was really pretty primitive, but the software architecture and the software algorithms are what changed the world.
I think we all thought we were doing really interesting stuff, so it didn't really dawn on us that we were doing anything special.
Shaky established a position about what we should be thinking about as possible, as feasible.
To understand why Shaky is so important, we have to go back to 1966, and we have to understand where AI research was at that time.
Well, you have to remember that it was pretty much of a greenfield when Shaky started. All over the country and even outside of the United States, people were beginning to build the components to artificial intelligence. Nobody had tried at the time that Shaky was launched to integrate all the components of AI and robotics into a single moving vehicle that could reason about the world, could sense the world around it, and could take actions.
Prior to 1966, there were no robots, or at least not intelligent ones. The concept of an intelligent robot was limited to the realm of fiction.
You will meet a charming character in The Robot, always at your service.
When you read the title of the original proposal, it was something like a mobile automaton for reconnaissance. And the reason we called it an automaton was because until Shaky, you couldn't go to a funding agency and say, I want money to make a science fiction kind of device. So we needed a name. And finally, Charlie, in his inimitable fashion, said, it shakes like hell when it moves. Let's just call it Shaky.
Key components of Shaky's hardware were a TV camera to observe its environment, an antenna radio link, bump detectors, and a push bar to move objects.
My role was mainly get the images and get whatever coordinates they needed to determine where they were and extract the information from the image. I remember when I first saw it, gee, that looks like a dishwasher on wheels.
While charming, Shaky wasn't impressive for its looks. It was the AI and programming advancements that made it famous.
We structured Shaky software in 4 distinct layers. And that was the first time that a layered architecture was used for robots.
Shaky's pioneering software architecture paved the way to a new era of AI and robotics. The SRI team later developed Flaky, a research robot that demonstrated fuzzy logic and goal-oriented behavior. Then came Centibots, one of the earliest projects in swarm robotics, where 100 autonomous robots demonstrated the ability to map a complex area collaboratively.
I like how it's code that isn't just turning numbers into other numbers. You get to see the thing come to life right next to you.
Shaky also inspired research in natural language-based interactions, leading to the popular speech-based technologies that we use today. Shaky's breakthrough in computer vision is now used to help drivers stay in their lanes. And every time you get driving directions on your phone or a navigation system, you are benefiting from the A-star navigation algorithm, first invented for Shaky. Even NASA's Mars exploration rovers use navigational techniques that were first launched with Shaky.
The future is things like potentially having teams of autonomous aircraft that could go out, for example, and do firefighting, and doing this either fully autonomously or potentially in tandem with human-piloted aircraft that can go out and work with them collaboratively.
Shaky now resides in the Computer History Museum, visible to hundreds of thousands of visitors annually. And in 2017, Shaky was honored with an IEEE Milestone Achievement Award.
The Shaky milestone is important because, first of all, Shaky is the world's first mobile intelligent robot. In addition, this is the first IEEE milestone in the areas of either robotics or artificial intelligence.
Looking back, more than 50 years after the Shaky project began, it's inspiring to see how one small team can make such an impact. How one ambitious idea continues to benefit our lives. How one robot changed the world.
We didn't realize, I think, any of us, what the significance of this was. We knew we were the first, but nobody knew where it was going, and I don't think any of us would have predicted what happened.
Shaky planted the flag way out there. It's a model of the kind of ambitious projects that we should be looking at in the future.
All right, so that was Shaky's video. It is actually in the Computer History Museum down the road. So when things open up, like I suggest going there and seeing Shaky there. Cool. So that was my quick history of robotics. If any questions comes up, just feel free to ask now or later. And so in the next part, what I'd like to do is I'd like to talk a little bit about how is this related to some of the topics that we are learning through this class. So how are robots in general like using ideas around AI? And I want to spend a little bit of time on that. So if you think about robotics, there's this common architecture that is usually used for robots. It's more under question these days, but back in the day, actually, like this was the architecture that a lot of robots tend to use, which is the sensing, planning, and acting architecture, and then looping that, right? So you sense the world, you watch the world, you perceive the world, you do perception, and then from that, you try to plan on what to do next. That is where the intelligence lies. And then after that, you just act, you execute that plan. And then once you've acted, like you can go back and sense, plan, and act again. And that's a very common architecture that most robots do use. And then these days, people are thinking about a more intertwined relationship between sense, plan, and act. For example, you shouldn't just sense the world for the sake of sensing, right? Like sensing needs to be active. So there's this area called active perception, which is about the fact that I only sense the parts I care about and I need to act on. And we should have like this intertwined relationship between acting and sensing. Or there's another paradigm these days that basically tries to go from images to actuation and kind of like skip that planning part of it by replacing it by neural networks, right? So if I have a machine learning system and I start from images, can I get directly a control on my robot? That's another paradigm. I'll talk about that a little bit actually in this section. But let's just consider this type of paradigm of sensing, planning, and acting. And in this class, starting next week, we're going to first talk about search. And actually, as you heard in the video, we're going to talk about algorithms like AI star. That's actually something that we will discuss next week. And AI star was introduced for Shaky, right? Like the point of it, it's actually like an extension of Dijkstra's algorithm. And it does have a bunch of heuristics and is fairly fast. And it was introduced for things like robots moving around and navigating around. Today, we do use a lot of sampling-based type techniques. So the algorithm that you see here running is this algorithm called RRT star, which is similar to A star to some extent, but it's more of a sampling-based algorithm, creating this tree, this dense tree, and navigating along the lines of tree. So the type of things we will be talking about next week, search, actually falls a bunch like in planning for robots, right? Like when you're planning for robots, you should think about searching in that space. How do you get from one location in the space to another location? Or how do you get from one robot configuration to another robot configuration? Following search, the week after, we're going to talk about MDPs and games, right? MDPs are Markov decision processes. Basically, the idea there is the world has uncertainty, and we should actually model those probabilities and uncertainties. And that commonly shows up when you think about robots interacting with each other or with the world in general, right? Like when you have dynamic environments around you, when you have a self-driving car driving right next to other cars, right? That you can model that as an MDP. And similarly, if you think about this interaction with another intelligent agent, you can model that as a game. And then we'll be discussing that in a couple of weeks. And these ideas show up a lot in robotics. So here, the video on the left basically shows two robots that are trying to coordinate with each other. And what they're trying to do is they're trying to move this rod together. But the interesting thing is that they're decentralized. They don't talk to each other. And they have different observabilities. So the robot in the front can see the books here, and the robot in the back can only see the boxes. And just because of the forces and the feel of the forces, they can understand what the other agent is doing. They can learn what the other agent's policy is and coordinate with that agent to do this collaborative type of maneuver. Here's another example. This is also from my lab. So here what we are looking at is we are looking at two robots playing air hockey. And here we are, again, like having this paradigm, this game theoretic paradigm of two robots trying to coordinate with each other. There's a bit of more learning happening here. So the robots are trying to, again, learn the policy of the other agent or representation of the policy of the other robot. And based on that, like kind of trick the other agent or influence the other agent and win this air hockey game. So, okay, so MDPs and games pretty much show up for any type of interactive systems. And as robots are leaving factory floors, they have more and more interactions with people or with other agents. And they're super useful, again, for the planning part of robotics. We will see Bayesian networks immediately after that. Bayesian networks, again, are super useful when it comes to things like mapping and estimation. So here, there's this algorithm called simultaneous localization and mapping, SLAM. And basically, the idea of it is that when you go to this new environment and you don't know anything about this new environment, you're going to sample points. And based on that, you're going to create a map and navigate yourself around it and estimate where you are. So a lot of ideas around Bayesian networks shows up here. Actually, in one of the homeworks, we were going to look at things like particle filters and things like state estimation. And based on that, how do we use ideas from Bayesian networks to do better estimation of where we are, where other agents are? And again, that is super useful for any robotic system that tries to like do anything in the world, basically. Okay. All right, so a lot of that was around planning. Logic is also another topic we will discuss in this class. It is not as much used in robotics, but it does show up at various places. So here, this is actually a work by Chris Gazit's group, and this is called LTL Map, which is basically a tool. And the idea here is they try to get this robot navigate this space and go to various squares here. And while doing that, it tries to satisfy some logical formula. So instead of giving it an objective, a loss function, and then doing gradient descent, let's say, on that, and try to come up with a policy, what this robot does is it gets that logic formula, and based on that, it creates a plan on how to navigate this space. And why would anyone want to do that? Well, the reason why would anyone want to do that is if you have that logic formula, you can actually prove things about this robot. You can actually prove that if it would satisfy this specification or if it wouldn't satisfy this specification. And again, that is very useful when you think about safety of, let's say, autonomous cars, right? If you want to prove that your autonomous cars are safe, you would need to add a little bit of logic there. You would need to think about how that can be used in planning. And it also helps with transparency, because there's a smaller gap between, let's say, natural language and temporal logic, which is this logical language that they're using here. And that smaller gap can help us like have a more transparent and clear idea of what the robot is doing here. Okay. All right. So that was all planning and all the topics that we are discussing in this class. We are currently talking about machine learning. A common place that machine learning shows up in robotics is on the sensing side of things. So you sense the world, and based on that, you perceive the world. So perception and vision is a big part of robotics, and a lot of that is done using machine learning these days, right? So you have a machine learning network that basically tries to do object recognition and activity prediction of what other objects around you are doing, or basically like who's the owner of the car in this case, I think, and what are the other objects around us and things of those forms. So that's a very common place that machine learning shows up in robotics, in the sensing and perception side of things. And you might ask about this acting part. Well, what goes in the acting part? So it's not just AI that shows up in robotics. A bunch of other fields also show up in robotics, specifically control theory and optimization is kind of like the core of this acting component of this architecture of sense, plan, and act. And basically the idea is you might again have an objective like following a trajectory, and you actually want to put the right control, the right accelerations and throttle and steering angle on your autonomous car in this case, and get your autonomous car to navigate around. Let me turn off the audio here. And a lot of that, a core of that is actually done using ideas around control theory. More recently, people have been using ideas around machine learning here too. So like adding ideas around deep learning for actually planning and getting the car to navigate in this space. So those are some of the core ideas. As I mentioned earlier, there are some other paradigms of the sense, plan, and act. One specific paradigm, which I think is pretty interesting, is to use machine learning to do kind of like this, all of this sense, plan, and act by trying to learn from humans. Okay? So this is commonly referred to as learning from demonstrations or imitation learning. And the idea of it is if I just watch how humans do things, then from that, I can just directly figure out what their objective was or what their policy is. And the idea has been around since like 2000s in the area of robotics. The work on the left that I want to show is actually like this idea directly being applied to robotics. This is work that Peter Abeel and Andrew Ng did in 2004 at Stanford. And basically the idea is there are basically these helicopters that before then, it was really hard to fly them by just using control, like by just using like AI and control. It was actually just really hard to fly them. And then there are these pilots that can fly these helicopters just much more easily, much more simply. And basically the idea is, could we use that here to get this helicopter to fly in this space? So this is Andrew.
What the helicopter does is it watches a human pilot fly the helicopter around for a while. And by watching a human pilot learn to fly, it then learns to fly by itself. And so what it does is it watches the person fly, and then it will try to fly the same stunt maneuvers by itself, and maybe try a few times until it sort of nails the maneuver. And what you're seeing is the end result of this machine learning process called apprenticeship learning.
So that was this idea of apprenticeship learning, where kind of like for the first time, like people were able to fly these quadcopters autonomously, but by learning from human pilots, by learning from human experts. And that idea has been around in research, and people in general have been thinking about how we can learn from humans. How can we get robots to act in the world by directly learning from humans, but not just from demonstrations, but also from things like asking their preferences or language instructions. So in my lab, actually, we are doing a lot of work in this domain where we were looking at preference-based learning and actively basically querying people for what their preference trajectory is in order to basically get a robot to play some version of mini golf here, like targeting for one of these balls and get the robot to actually hit the ball correctly so it gets in the right ball. And that's kind of exciting because you can learn from all sorts of human feedback, right? You can learn from demonstrations, comparisons, language, and from that you are able to basically get a robot do an interesting type of maneuver. Another place that machine learning shows up is, again, like by combining this sensing, plan, and act into one giant box, right? Like starting from visual data. And once you start from visual data, can you try to directly get actions on your robots? And this idea of robot learning has been very popular in recent years. This is work from Berkeley from 2015, where basically the idea is you get the robot to just try out things. And then from that, from these images and kind of joint angles of what the robot tries, from that it learns how to achieve the task and how to do the task. It's a very data-intensive type of process, but there's a lot of excitement because you can achieve things that you weren't able to achieve before. And we have seen a lot of advances in machine learning when it's applied to, let's say, NLP and vision, places where we have a lot of data. We don't have that much data in robotics, but if that is the bottleneck, then maybe we can create an arm farm, kind of like this image, this video here. And create an arm farm and basically just collect lots of data of robots basically like navigating in this space, moving randomly inside of this box. And from that, learn how to just grasp any object that we see. This is actually work by Google Robotics. So Google X has a subgroup, Google Robotics, that does a lot of work around robot learning, a lot of interesting work. And yeah, like very intensive, very compute intensive, but lots of excitement around this idea of directly learning actions from sensing data. Yeah. All right. So let me move to, okay. So those were all the things I wanted to say on how AI is used in robotics, but AI is not the only thing that is used in robotics. There are a bunch of other things, like as you've probably noticed, robotics spans a bunch of different departments. For example, you see robotics in mechanical engineering, and that has a very different view of robotics. And that view is usually focused on design and co-design, which is a super important problem, right? So if you're thinking about building an arm or building a hand that needs to do very precise manipulation, what type of sensors you're using, how are you building this system? Like those are all really good questions. Like how do we make sure that you build a prosthetic that is not too heavy and is also comfortable and is also very safe for the person to use for walking? Like these are all really great questions that are usually like design questions that are super important in robotics. Another reason that this is important is that there's a whole new area around co-design, which basically says, well, for whatever hardware we pick, there's going to be some AI algorithm, but if I change that hardware, my AI algorithm is going to change. And if I change my AI algorithm, like that could run on a different hardware very differently. So can we design both of these at the same time? Can we design what our robot should look like and what algorithm should run on them kind of at the same time? Or can we have reconfigurable robots? And there are a lot of excitement around this area in general when we think about design and co-design of these systems. I just want to show a few other cool designs that are out there that are very impressive. One design that I want to show is this robot on the left. This robot on the left is a dynamic integrity structure. So what it is it basically has a bunch of rigid links like these guys. And then these links are connected by things that are kind of like ropes. And it's kind of like a funny structure. But the interesting thing about it is it is shock resistant. So like NASA really cares about this robot because landing robots on the surface of Mars is really difficult. But if I just drop this robot, like nothing happens to it, and it can just roll around and continue moving forward, which is again a very interesting design for something that you don't want to break, because robots in general are pretty rigid, and this robot is very flexible. So there's a lot of interest in basically building robots that are softer, that are less rigid, that are flexible, and this is an example of that. Another robot that I think is kind of fun, I'll show this a little bit later, a video of it, is this robot from Stanford. This is from Mark Kotkowski's lab. And it's called StickyBot. It's basically a robot that has kind of gecko-like hands. So its hands are inspired by like hands of gecko and having like these suction cups. And because of that, it can climb up like walls and really like slippery like slopes, which is again a very interesting design. Another design that I find super interesting is this inflatable snake robot. This is from Alison Okamura's lab, again in the mechanical engineering at Stanford. And the idea here is that this robot can inflate itself as it goes through different parts of the environment. So it might be really difficult, for example, to go through this hole, but like as the robot is inflating, it's actually making its way through different like kind of narrow spaces and getting to various areas of the space. This can also be used inside of our body. For example, when we are doing like more intelligent type of like endoscopy, like we can actually send some of these robots inside of the body and navigate a little bit better inside of our body for robotic surgery, for things like endoscopies and so on. I can take any questions now, actually, about any of this.
I have a quick question. So you mentioned that robotic consists of like computer vision, machine learning, like embedded system. So what do you recommend for people who want to go into the field? Do you study all control theory and all those, or what's the role since a team?
Yeah, that's a very good question. Yeah, so it kind of seems like a giant thing, right? Like because it incorporates like everything. And the field of robotics in general, when you go to the conferences, it is interesting because you see people from all these different fields, but they're coming together for the same problem, but not the same technique, which is a very interesting kind of field to be in. But no, at the end of the day, like everyone just like focuses on their expertise and then brings it together as part of a team. So for example, robotics and CS, like at Stanford, I'll be talking about that actually a little bit, is a lot focused on developing AI algorithms, developing the algorithmic side of this, but they don't really like do as much on the design side. But robotics and the mechanical engineering is very focused on building new designs, new structures. And yet we do have a lot of joint projects where we use new designs and try to develop new algorithms for them, and lots of collaboration within these different fields. So it is a very interdisciplinary field. But yeah, as I said, it might seem too large. It's not that large. At the end of the day, everyone focuses on the thing that they're actually like very interested in for the same goal of building robots.
Thanks. I have a question.
Sure.
What subfields of robotics would be really great to go into a startup for right now?
So to start it, right? Is that what you? Yeah, so that's a good question to ask. Yeah, so I think there's a lot of excitement around autonomous driving, right? So, and autonomous driving these days is very focused on like vision and machine learning and control theory. So like those three kind of like backgrounds are commonly used in autonomous driving. But beyond autonomous driving, I think like, and a lot of big companies are using them, so it's not necessarily startups. But beyond that, yeah, so people are very interested in domestic robots these days, right? Actually, like getting robots inside people's houses, which wasn't the case like a few years back even, right? Like we have robots functioning very well on factory floors, but having robots in our homes is a big problem. And there were some startups that weren't very successful. So it's kind of like an edgy area to be in. But I think there's a lot of excitement there, like home automation, like things like kind of next generation Roombas or other things that we can have in homes. And again, for that, I think like a lot of these systems are using machine learning AI in general. So that is, again, like a huge like background that you would want to have. But then design is pretty important there. So like the type of like hardware design that you use there is actually super important. Yeah, and healthcare, like kind of like thinking about robotics being used in healthcare and hospitals and things of those form. I think that is also a very exciting area.
Got it. Thank you. Can I ask a question?
Sure, yeah.
Yeah, so it's kind of like co-op. So it's about like robotics, like research. Because right now, like as you said previously, like there's a lot of things like happening in AI stuff, and also like there's also like something happening like in control theory. Mm-hmm. So is there any research kind of like moving these two things together? Because for my undergrad, I study some like control theory and also AI, because I find out like in control theory, they have like some really interesting concepts actually, like stability, like observability, like all of this. So have you like there any research like, for example, using these concepts to do, for example, like reinforcement learning setup in like learning setups, which is missing like a stability or like some concepts like this? Is there any research about that?
Yeah, there's a lot of excitement actually around that. And I totally agree with that, right? There was a lot of interesting topics in control theory. There are a lot of interesting topics in AI and machine learning that are just making their ways into robotics. And the two communities, at first there was a little bit of like clashes between them, I would say. But now I think there's a lot of like coming together and trying to combine those ideas. There's a new conference called Learning for Dynamics and Control of 4DC. And the whole point of that is actually bringing learning people and control people together to try to use the same ideas. Yeah, lots of research trying to bring learning and control together. And I think that is actually the right direction because, as you said, lots of interesting ideas in dynamics and control. And I think a lot of those ideas could be used as prior structures that could be put on learning-based systems. So when you're, let's say, training a neural network, you can bring in structure that you know about the system that comes from control theory, let's say.
Thank you.
Mm-hmm.
I had a question.
Sure.
Sure. I was wondering, you talked about ARM farms and, collecting lots of data. Do you feel like the field is more data limited or more algorithm and learning limited? I think about when I learned to drive, it wasn't that maybe it should have been more data, but it wasn't. It was just maybe a couple of weeks of practice, and then I was ready.
That's a very good point. So I think it's a combination. I do think the field is very data limited. And it's interesting because, when you learn to drive, right, you spend a couple of weeks, but you have seen cars drive right next to you, like the learning by observation, which is like a very interesting type of learning. You're not learning by doing, you're learning by like observing other people like drive right next to you. And that has so much information in it. It's kind of the same problem that I mentioned earlier with the House of Cards example, right? Like your autonomous car doesn't know that it's important. But like you would know that you have so much context like in the world. And because of that, like I think like the issue is specifically for autonomous cars is some of these corner cases. So like driving on a highway, like that's like solved, right? The issue is like some of these corner cases that it hasn't seen yet in the data, and maybe more data will solve that. So I think more data is definitely a problem. I think we can still do better on our algorithms too, but data is still like, I would say that's the higher kind of like issue, at least in autonomous driving, I would say.
On the data side, do you feel that synthetic data could be something that would be useful for machine learning applications, or is that something that's kind of like going to always be a fantasy?
I think it's super useful, right? Like if you can create near accident driving scenarios in driving and then kind of train your car in those settings and then just generate that automatically, that would be super useful. So then you don't need to wait forever to see like a near accident driving scenario on the vehicle. I think one issue there is like this simulation to reality gap, which is a big problem specifically for robotics. But I do think generation of data is important. Yeah.
Hi, so I have a question regarding the non-determinacy of robotics. For example, in terms of machine regulations, like government usually requires that the actions of a machine to be deterministic, and the manufacturers of the machine are sometimes responsible for these actions. But with a machine learning-based or deep learning-based algorithms, they are statistical by definition. So how do we define the responsibility of the manufacturer of the machines, and if there's accident caused by autonomous driver, who should be responsible in this case? Yeah,
that's a very good question for Tino next week, actually. So very good question. So the first point that you made that like all the laws are about deterministic systems. That's actually not like always the case. So for example, Michael Kokendorfer in the Aero and Astro department, he has done a lot of work around MDPs that actually run on like aircraft systems. So there's this ACAS XU system, which is basically unmanned like aircraft, like all of the motions landing and taking off and all of that is done in kind of like an unmanned setting. But the system is small. It's a POMDP with like a few states and all that, and you can verify everything about it. So there's a lot of interesting rules around verification and validation in this space. And even if it is not deterministic, you can still like verify it. So the small POMDP, for example, partially observable Markov decision process. You won't see that in the class. If you're interested in that topic, take Michael's class. But when it comes to neural networks, we don't really have that much guarantees around it. And there's a lot of, again, discussion here. So some people are taking the route of trying to prove things and trying to verify neural networks. Clark Barrett is someone in the CS department who does a lot of work around verification of neural networks. Again, we are limited in the size there, so we can't have giant neural networks there. Another kind of perspective on this is giving these statistical guarantees, right? Like if my autonomous car is safer than humans statistically, maybe that is good enough and we are okay with some number of accidents, some number of times. Maybe we would be okay with that. And some of it is, yeah, like acceptance issues too, right? Like the first like aircraft that were out there, probably not safe. Probably people were okay with that, and the number of deaths were like higher, right? And I think there was a little bit of that acceptance issue for how this is going to pan out. But it is actually a very good question of how are we going to regulate and who is going to be at blame. One can take Tesla's approach and be like, hey, human is always in control, so if anything happens, it was a human's fault, which is kind of like a weird type of approach, I would say. It's not necessarily the safest way to go. But yeah, I don't honestly have good answers for this. Something to ask Tino next week.
I have a question with regards to the co-design. Mm-hmm. So you mentioned about the hardware and the AI algorithm needs to go hand in hand. So, for example, the self-driving car has to make, the algorithms have to make quick decisions with the real-time change in the environment. Mm-hmm. And if the algorithms take a long time to run, and I know the hardware-wise, there are a variety of ways the algorithm can be put on, let's say, on a GPU or on other aspects. So would you please, are there any pointers towards how these two go hand in hand, and what is the best way to do that?
Yeah, so I was more thinking about it in an offline kind of fashion, right? So in an offline kind of fashion, you can have like a fancy algorithm that does like everything, like that takes a lot of compute, let's say, for a hardware that is very simple. Or you can kind of like increase complexity of your hardware, and on the other hand, have a really simple algorithm that runs on it. One place so I wasn't really thinking about the online aspect of it, which you're right, like, yeah, they're like running at different frequencies, so how could they work together? One example of that is in assistive robotics, so assistive teleoperation, when you're using a joystick to control a robot arm. This is something that we work on commonly. And you can make the hardware very interesting, very intricate, like use haptic devices, and then be able to control things like much easier. On the other hand, you can have a hardware that's really simple. So for example, there are these sip and puff devices that a lot of patients with disabilities use. And it's a very simple device. You can only like sip and puff. Like that's the only thing you can do. But then the algorithm that's underneath needs to be like much more complicated to be able to capture what that sip and puff means. So that's kind of like one place that this interplay between hardware and algorithm really shows up. All right.
Thank you.
Of course, yeah. Let me continue a little bit, and then I'll stop at the end of the section, and I can take more questions too. After that, I kind of want to show some of these applications too at some point. This section is small, so the robotics at Stanford one. Yeah, so we talked about all of these. We talked about the history. Robotics at Stanford had an interesting history too, so it does have like an old history. Here's a video that I kind of just wanted to show for fun. This is a video from Osama Khatib's lab. Osama always has the best videos. He has these two robots, Juliet and Romeo. The other fun thing in this video for me is lots of these people are like faculty now or like very famous in the field. So it's kind of fun to see them as grad students at Stanford. So yeah, this is like Oliver Brock. This is Gates. If you like look at it closely, it is first floor of Gates. It hasn't changed much. This robot is still on the first floor of Gates. So if you get a chance to go there, it is still like somber. And yeah, like this is basically getting this robot helper to help you do various sort of things like move object for you. They had basically two of these. Let me move forward a little bit. So it helps you like carry objects and things of those form. It's a very old robot. And some of these concepts that we study like now, even like thinking about interaction between humans, like they were thinking about this back in the day. This is collaborative transport. These robots are not decentralized. They do actually have a centralized control, but they're compliant. So meaning that they're not rigid, right? Like if you move it, like they also get moved. Yeah, so I think, and then later on, there's this video of dancing with Romeo. So again, it's compliant and it kind of moves around you and all that. So this is some old videos from Stanford Robotics. Some more recent videos of Stanford Robotics and successes, I guess, is about the DARPA Grand Challenge. So it's not that recent. It's from 2005. So DARPA Grand Challenge was this competition that DARPA put out, and basically it was a competition that was trying to get researchers to work on autonomous driving. And this was basically the competition in 2005, where Sebastian Thrun was heading the Stanford team, and Stanley was the vehicle, and actually won the competition. Stanford logo.
In case you don't recognize it, that is a Volkswagen Touareg coming into the finish line configuration. Ladies and gentlemen, boys and girls, it's been done. How about that?
So that is Stanley passing the finishing line. After this, actually, Sebastian Thrun left Stanford and joined Google and started the Google self-driving car group there, now Waymo. And yeah, lots of advances in autonomous driving since then. But this was kind of one of the big successes of Stanford Robotics, winning basically this DARPA Grand Challenge, which was very exciting. But in general, robotics at Stanford kind of falls into a bunch of different departments. So in computer science, here are some of the faculty. I just wanted to show their faces so you know who they are, and you can take classes from them later on and things of those form. So Usama Khatib, I've already showed a lot of videos from his lab. I have one more from his lab that I'll show later. And Usama does a lot of work around field robotics, meaning that I'm going to send robots to places that humans haven't seen before and see what happens, which is like really exciting. Then we have Ken Salisbury, who does a lot of work around like helper robots and building systems that can actually help people. Silvio does a lot of work around vision and robotics. So he's primarily a vision faculty, but he is thinking about that intersection of vision and robotics. And some of the more recent people who've joined, including myself, Jeanette, and Chelsea. So Jeanette does a lot of work around manipulation. I'm personally very interested in interaction. So when you think about multi-agent interaction or interaction with humans. And Chelsea does a lot of work around robot learning, meta learning, and things of those form. In addition to some of these faculty, there are some other folks in the CS department who do a lot of work that is related to robotics. So again, Fei does quite a bit of work in vision, but also is interested in robotics, that intersection. And then Karen Liu and Jiajun Wu, both of them recently joined Stanford, and they do a ton of work around physical simulation, graphics, things of those form. And that has a lot of relations to building robots that can work with, like I'll say, deformable objects and things of those form. And some folks who used to do robotics, I guess, are Andrew and Sebastian. So I showed a video of Andrew's learning from demonstration work earlier, the flying video of the helicopter. And then Sebastian has done a lot of work in autonomous driving. They're both kind of around. So Andrew does a lot of work in healthcare these days. Sebastian comes in. He's an adjunct faculty now. Outside of computer science, we still have a lot of robotics faculty. So in the Aero Astro department, we have Grace Scow, Max Schrager, Marco Pavone, and Michael Kokendorfer. I mentioned Michael's work around aircraft systems earlier. So building these ACAS-U systems and trying to prove properties around them. They all do a lot of work around drones and quadcopters and helicopters, things of those form, multi-agent systems, and being able to give guarantees and talk about risk. And finally, in mechanical engineering, we have a good number of faculty: Alison Nakamura, Sean Fulmer, Mark Kotkowski, Steve Collins, and Monroe Kennedy. A lot of them, like almost all of them, do quite interesting work around design too. So building systems that are actually like interesting and useful. The sticky bot that I showed earlier was from Mark's lab. The snake robot was from Alison's lab. Sean does a lot of interesting work at the intersection of robotics and HCI. So if that is something you're interested in, you should check out like what these faculty teach and all that. So that was kind of my very quick robotics at Stanford type of overview. Let me spend another 5 minutes showing some of these applications, and maybe after that, I'll take questions for the last 5 minutes. And I have a 7-minute video that I'll just leave after the class for you guys to watch. It's like a 50-year like history of robotics, which is kind of fun. All right, so I wanted to show you basically generally some exciting applications of robotics. And I actually had a hard time classifying it because I think classifying them they can be classified with different axes, and it was hard to classify them. But I ended up classifying them into 3 main groups. The first group is bio-inspired robots, which is basically, let's look at biology and try to build robots that are useful. So a lot of interesting design goes there. Another interesting direction is soft robotics, meaning that, hey, I'm going to build systems that use soft material. So the tensegrity structure was an example of that. So they're flexible, they're soft, they're not rigid, they're not going to break. I'm not going to actually talk much about soft robots, but I'm going to talk about manipulating soft objects, which is a very difficult algorithmic question. And then finally, if I have time, I will talk a little bit about domestic and interactive robots, which is something that I think is really exciting. Like this interaction with humans is something that you should really care about as robots are basically starting to interact with us. All right, so bio-inspired robots. This is more of a interesting design question. So from kind of early on, everyone was interested in humanoids because you want robots to look like humans for some reason. So there's a lot of work around humanoids and building robots that look like humans. That is, they have 2 arms and 2 hands and 2 legs and a face. But at some point, people realized robots don't need to look like humans. And they started looking at the nature in general and started thinking about generally bio-inspired robots, right? There are a lot of animals that can get to places that humans can't, and can we build robots that are similar to them? And another interesting topic that shows up here, specifically under humanoids, is this idea of walking. So people have been obsessed with walking for years now. And it's an interesting problem. Like if you want to build a robot that walks kind of like humans, that is still very difficult. Like all walking robots have like weird gaits and they don't really like walk like human-like. And when they do, they're just super inefficient. Like humans are just amazing at walking. And that's in general a very active area of research, trying to get robots to walk. And why do we care about that? Well, first off, it's an interesting question. Second, like building exoskeletons, building systems that can help people walk is always an interest in this field. So let's look at a few bio-inspired robots. I only just want to show a lot of videos of these systems. So one type of bio-inspired robot is looking at insects like cockroaches and try to build robots that kind of act like cockroaches because they're amazing at getting through like obstacles. And there's a team at UC Berkeley, Ron Fearing's group, that basically designs robots that are similar to cockroaches, and they go through places like cockroaches. And the nice thing about it is, yeah, they're very agile, they go through things. The other thing is they're small and they can be super fast. So you can have like a swarm of these robots get to places super fast. And another interesting thing about cockroaches is when they navigate, they use their antennas. So that is actually how they figure out where the ball is. Like using the antenna, they figure out, they kind of like follow the ball. And basically people in Ron's group have been using similar type of ideas to be able to sense the world and actuate in this world. And they even build these robots using origami, which is kind of interesting. But it makes sure that they're small and they don't take as much battery power and energy, and they're kind of like light. Let me actually move to this one. The other robot that I showed you a little bit earlier is a bio-inspired robot, is the Sticky Bot from Mark's lab. So basically, if you look at gecko feet, it has these suction cups it's very, very tiny suction cups that gets attached to glass. And because of that, like this robot is using a similar type of paradigm, and it can just like walk up like really slippery slopes, like polished granite. And that is super impressive thing. So lots of cool design going on here. Similarly, I think snake robots and eel robots are very popular. There are a lot of like links connected to each other and they can navigate easily. This is an eel-like robot. It's an underwater robot. It does have a camera in the front, and based on that, it navigates, which is kind of cool. All right. And then this is a hopper. So this is basically a robot, again from Ron's group, Salto, which is kind of like jumps around like a bush baby. It's kind of cool. if you guys have used things like Mujoko, which is a simulation environment, you might see these random animals in Mujoko. Part of it is roboticists care really about like different types of animals, like swimming type of motion, hopping, and that's why those show up in this Mujoko type environment, which is a simulation environment, physics simulator that allows you to train things basically in simulation. All right, so those were generally bio-inspired type robots. As I mentioned earlier, we've been obsessed with humanoids, so lots of energy and money goes into building humanoids. Honda actually spent a lot of money on building this robot called Osimo. Its walking is kind of weird.
Hello, everybody.
Hello, Osimo.
Hello, Mom. It's nice to see you.
It's nice to see you too, Osimo. I am happy to be here with you today.
Thank you. I'm excited to be here in Washington, D.C.
The all-new Osimo received a...
All right, I'm going to cut it there. But yeah, so humanoids have been really exciting. And another place that actually humanoids show up is basically when you have... one other example I want to show basically is sending humanoids type robots to spaces that you wouldn't be able to send before. So I want to show a video of this robot from Usama's group, Ocean One. Some of you might have seen this video. This is basically not a full humanoid. It does have 2 arms, so you can teleoperate it and get the robot do various things. But it goes underwater to places that people have not been able to go before. So let's just quickly watch this video. It's kind of like a nice video of Usama's work.
Ocean One is aimed at bringing a new capability for underwater exploration. The intent here is to have a diver diving virtually, creating a robot that can be the physical representation of the human. A humanoid robotic diver that can have bimanual capabilities. So it has 2 hands, it has stereo vision, and the most amazing thing about it is that you can feel what the robot is doing while it's sitting up on the boat. And this is combining the technology of haptics, that is the idea that we can reflect the contact forces. It's almost like you are there. With the sense of touch, you create a new dimension of perception. This robot is oil-filled. It allows us to take the robot very deep. This robot can go to thousands of meters.
This is Stanford pool,
truly a human-like machine that is also human-friendly. La Lune is a 17th century shipwreck located about 20 miles off the coast of Toulon in France at 100 meters. In the last year, we have been working and getting our robots ready to take on that expedition. And we are going to land on the moon. More than 70% of the surface of the planet is water. We have a lot of structures, a lot of coral reefs to monitor. We need to reach down there. You can think about it as a solution where we
given that I don't have
the human from
that much time, I'm going to kind of like move forward because probably the last thing I want to show is the walking video, and then I'll close it and ask for questions. But yeah, like in general, if you're interested in underwater robots, Usama does a lot of work around that. He's at Stanford. He teaches classes. Talk to him. I think that's a very interesting direction. And then finally, I guess the last video that I can show under this category is this idea of walking and jumping and things of those forms. So, so there's a lot of, again, excitement around that. And Boston Dynamics, the first video I showed you guys for the dancing robot was also from Boston Dynamics. Does a lot of work around building very dynamic robots. So they have really good controllers for these robots. And this is Atlas from Boston Dynamics. Jumps. flips even. That is super impressive. And usually roboticists show that one video of it working and don't talk about videos of it not working. But more recently, people are showing more videos of things not exactly working. So I think this video, it's super impressive how it recovers, because that is really hard to do in real time. That was a failure. So yeah, so okay, so lots of excitement around these areas. I can start taking questions now. I'm not going to show more videos. I have more stuff to show, but let me just answer a couple of questions, and then I'll just, at the end at 2:20, I'll leave this video of 50 years of robotics that Osama put together and has fun music. So any questions?
I had a question. I was super impressed by the last video you showed of the robot doing flips. I was wondering, it looked really heavy, like it had a lot of materials, and I was wondering if why they chose to equip it with such materials. I thought, maybe using lighter materials so that it could be easier to jump. I was just curious if you knew the reason behind how they designed that robot.
That's a very good question. Yeah, so I don't know the details of it because I don't personally work too much on walking and the design side of things. But yeah, I actually don't know what material they're using. They definitely do consider different types of material and making sure it's lightweight and all that. But I think there's just a lot of joints and a lot of stuff going on with that robot. If you're interested to learn more about that, yeah, check out Boston Dynamics, basically website. They have all their cool robots there.
I have a question. So I was wondering, what's some examples of state-of-the-art research involved both robotics and NLP or language-based AI? For example, voice-activated systems or related work?
Yeah, there's a lot of excitement around actually NLP and robotics. I actually have a student joined between me and Percy, which is very exciting. This is first time doing NLP and robotics together. There's a lot of work around instruction following. So basically just making an interactive teaching. So when you have a person and a robot at home, how would the robot learn that you care about House of Cards or you don't care about House of Cards type of a thing. So thinking about human-robot interaction a little bit more carefully when you actually have access to NLP. So that is one place that it shows up. Another place that is a little bit harder to think about, but I think it has a lot of value, is thinking about the large data set of natural language data that we have generally. We have a lot of text data, and from that, if you can learn something about context, learn something about how a robot should cook an egg. I think that is very interesting too. And I haven't seen that much work around it, but again, lots of excitement in that particular intersection of NLP and robotics.
Hi, I had a question as well. Maybe this goes more into the scope of visual recognition, but robots will be playing a part in this too. So the world, unfortunately, will always consist of good factors and evil factors. And for international security purposes, there will be a role, or if there already is a role, for robots and autonomous systems. But those same methods can unfortunately also be used for human rights violations too. How do you build it so that, technology will always be neutral. It's its use that determines what the outcome is. But in the case of human rights violations, how can you build systems so that an authoritarian regime, or what would be the way to using technology to evade an authoritarian regime that will have the best technology? I've seen some works around how to fool facial recognitions. How can technology work against technology when it's needed and also serve its purpose when needed? I think it's a tough question.
It is a very tough question. I refer that to Tino next week specifically. But in the case of vision and in the case of using ML, in general, machine learning, I think it is much tougher. In the last lecture, I will talk about this a little bit, this idea of fooling neural networks. There's some recent work around basically showing that you can always find adversarial examples. So this idea of trying to safeguard your system so it doesn't get affected by adversarial examples is just not going to work. There's this proof by Audition Year and others who have actually shown that you can always find basically an adversarial example in some settings under some distances. In the case of robotics, I've been part of some discussions around this idea of autonomous weapon systems, as I mentioned earlier. For those discussions, there are discussions on the number of drones that, for example, can be purchased at the same time and things of those form. A lot of concerns there is basically autonomous weapon systems becoming weapon of mass destruction, which is kind of scary, like as I talk about it. But yeah, like discussions around that is what sort of limitations can be put, what sort of regulations can be put there, so like people don't buy too many drones at the same time and weaponize it, let's say, like things of those form. But I'm definitely not an expert in this. I refer you to Tino Hoyler next week on more details on this.
Thank you. Thanks so much. I have a question regarding among all these, since robotics is such an integrated subject, like it integrates like mechanical engineering, artificial intelligence, and also power management, and also regulations. What is like the biggest limiting factor that prevent robotics from like affecting everyone's life from being like widely adopted?
By being widely adopted, there's still like dealing with uncertainty is still like so difficult, right? So like you have robots in factory floors, confined spaces, they can move around so much easily. Putting it in a world where humans are just like walking around it, there's so many reasons that the human could walk around it, and like figuring out what those reasons are can be really difficult. So in general, dealing with uncertainty, dealing with, in the case of autonomous driving, right, dealing with things like near accident scenarios that it hasn't seen before. All of those, like that uncertainty is like a big factor that's not allowing us to have robots like out there, like widely used in our everyday lives.
So given the current AI technology mostly are based on learning algorithms, but if you keep doing the learning algorithm, that means you can only like learn existing behaviors. So in order to deal with these uncertainties, are there any efforts to deal with uncertainties in life, or do some like a self-generated motion or self-motivated actions from the robots itself?
Yeah, so yeah, definitely. Yeah, so there's a lot of work around like actively generating these scenarios, active learning in these domains. So the robot but the robot still has some sort of hypothesis space that it can search in, right? So like you have a hypothesis space of things that can happen, and within that you can search. And yeah, so like there are these things that are called known unknowns and unknown unknowns. You can't really do much around unknown unknowns rather than like other than just randomly experiencing them. But for known unknowns, yeah, definitely like there's a lot of work on actively looking for the most informative data. I guess another reason that we don't have robots widely used is it's such an integrated system and it's such an interconnected system. So you have like the best AI algorithm and all of a sudden your camera fails. like the hardware failure can affect, like there's so many things that can fail in that pipeline that makes it just such a difficult system to debug. It's like everything coming together.
Thanks.
Cool. So, all right, so I'm going to just leave this video on, and then at the end of it, I'm going to sign off because it has fun music. Osama again made this. Osama is awesome in making music. But if you have more questions about these things, just come to the office hour, and I'd be happy to answer any questions. Let's just watch 50 years history of robotics, or if you guys want to sign off too. I'll talk to you later. This is 7 minutes. All right. All right. That was kind of long, but kind of fun. So this was for IFRA 2020. Okay. I still have 30 people. Oh my God. Okay. All right. Good seeing you all. That's it. I'll see you at office hours and our next lecture. Talk to you later. Bye.